Hello. We're going to go ahead and continue on with experiment number 7. And what this is today on this particular lecturette, number 7.5, is to discuss the second law, which is found on page 92 of your lab manual. What it says, a line drawn from the sun to any point or planet sweeps out equal areas of space in equal time intervals. These areas are called areal velocities. Let me make sure you understand this. So here we have, again, the moon is right here, focus and focus, major axis. And here is the actual orbiting path that the satellite has, is the ellipse right there. So let me explain what this is actually talking about. See if we can make sense of this. So I'm just going to go ahead and make the ellipse. Draw it like this. Here is the focus. Here's the other focus. Here's the moon right there. And let's say the satellite is right here, and I connect a line from the focus that the moon is centered on out to the satellite. And so what happens is I choose any type of time that I want to choose. A second, a minute, an hour, a day, weeks. So let's say it's just an hour. In that time, satellite will move in its orbit, and that line that connects the middle of the moon, the focus, out to the satellite, moves along with the satellite, sweeping out this area right there. So that line moves along. As it moves along, it sweeps out that area. We call that area Area 1. And then we wait some time. And let's say the satellite moves around its orbit, and here it is again. And again, we draw a line from the center of the moon at the focus out to the satellite. And this is a crucial thing, is that we have to use the same amount of time. In other words, we're comparing apples with apples. If we don't use the same time, then we're not comparing the same thing. And then we can't say much about this. So again, we wait 1 hour. And as that happens, satellite will move over there. And again, the line that connects the focus centered on the moon, connecting to the satellite, moves with the satellite, and it basically makes that area right there, Area 2. Area 1 and Area 2 are defined to be areal velocities. Just a fancy name for the area that line connecting the moon center to the satellite has swept out some given area for a given time, in this case 1 hour. So what does this law say? It says that Area 1 equals Area 2. Now we're going to have to talk about why is this the case. It seems relatively mysterious, and so we need to figure out what is the cause of this, and that's an important thing to actually figure out. So that's where we're going to go eventually. But first off, what we have to verify in this law, is this the case? For this particular satellite, are the areas the same? So I'm going to post another picture of the orbit. I've tried to make it as simple as possible. And so what I've done, let's see if I can get this to be illuminated as best I can. What I have here is I choose some time frame. And one thing I know is that there's, I believe, 15 minutes, let me double check, between every data point. And if you notice on the data table number 1, on the left-hand side, we see that there are times given, and every data point is 15 minutes apart. So what I've done is I've chosen a data point, then I've waited until 30 minutes pass. So there's a data point, and then a third data point, so a total of half an hour. And what I do is I draw from the center of the moon to the first data point, then I draw to the second data point, and in between is the actual area velocities. So that's area, I call it area A. And then I wait, and notice something though first, is I've chosen 2 points quite a ways away from the moon. So 30 minutes apart. And then I come down here and I choose a data point, and again I go 1, 2 more, and I have another area there. And so I have 2 different areas, so I want to compare that. Now, if you look on the bottom of page 92, there's data table 5. And what you're going to do is you're going to actually count all the squares that are between the data points for up here and down there. And there's no other way to say this, guys. Annoying and difficult. Because what's going to happen, to see if I can do this. Let's say I have a bunch of the squares right here. And here's some more squares. So I have the squares. And so let's say that I go ahead then and I have the lines coming out like this from the focus. So let's say that's the focus. And let's say the curve is like that, the actual elliptical orbit. So if I did this, I say, okay, let's see, there's 1 square, 2 squares, and I would have more, of course, up here. I'm just going to show a few. But now what I have to do is start estimating how much of a square these are. Maybe this is 0.9 of a square, right there, 0.9. Now here's a square right there. Here it might be 0.8. This might be 0.3. This might be 0.9 again. And so you have to start kind of estimating how much of a square is in here. You have to go through all of that and estimate as best you can. And so try to estimate the total number of squares that's between the line drawn from the focus centered at the moon out to the 2 data points. And then list those number of squares for both areas at the bottom of page 2. Just so you know, again, there's a data point right here where I drew from the focus out. Then there's another data point right there. And there's a third data point right there, so I draw then from there to there. That's 15 minutes, 30 minutes. So that's 15 minutes. And then 15 minutes, so we get a total of 30 minutes. I do the same thing here. There's a data point there, data point there, and a data point there. So again, 30 minutes. I've got to have the same amount of time. This right here, don't be mistaken, right here is the major axis right there. So the areas are given from the data points over to the focus centered at the moon. So that's what you do in order to get the 2 areas that you label on data table 5. Data table 5 are the 2 areas that you count the squares. Right above that, don't forget to list what time value you're using. I'm using 30 minutes. Then once you have those 2 areas, you do the same thing as you did previously for the Kepler's law number 1. Find the percent difference of those 2 areas. And again, remember the percent difference is where you take the difference of the 2 measurements divided by the average of the difference of the, average of the areas times 100%. So let me say that one more time to be clear. You have 2 areas given in data table 5. To get percent difference, because we're comparing the results of 2 different actual measurements, We're going to find the difference, take the absolute value. That means that this will not have a negative value. Divide that difference between the two measurements by the average of the two measurements. Remember how you average two measurements? You add them together, divide by 2. And that's all listed again on page 92 at the very top. And again, answer, is this going to be exactly 0% difference? And I would be shocked, because you're making estimates of these areas, and that's not the easiest thing to do. Will they be a huge difference? Well, there'll probably be a slightly bigger difference than Law 1, simply because this is a hard type of estimation that you have to make. But it should not be much greater than 20% or so. So if it's greater than that, then go back and re-estimate your areas. Yeah, guys, there's just no way to say, but this is a hard, annoying measurement to make. And again, why do we use the percent difference? Because simply we're comparing two measured values, two different areas. And because of that, we have to use percent difference. We're not comparing these areas against a true or given area that we count as true. So now going on page 93, so go through and try to answer those questions. Notice this. Excuse me. If I look at these measurements, notice this. It's up here measuring basically that far. Down here in a half an hour is measuring that or moving that far. Notice those two differences or distances are not the same. So if I go farther in the same amount of time as someone else does, am I going slower or faster? And I think the answer is obvious. If I go in an hour 60 miles and you go 30 miles an hour, I must be driving faster. This is going further here than there in a half an hour. Therefore, which one's going faster, here or there? The same reason is true. If I go farther in the same amount of time, I must be going faster. So this tells us something pretty amazing. It says, number one, is that the speed is not the same. So we have something we can learn from this second law when we make these measurements. What we can determine from this is the speed changes that the satellite's moving with as it moves around the orbit. That's the first thing. The second thing, where is it moving faster? Hey guys, is it moving faster closer or farther? I think the answer is obvious, isn't it? I go farther, I go shorter. Where must I be going faster then? So where is the satellite moving the fastest? You tell me. Or the slowest? You tell me. I think it's obvious by where we see the satellite is moving. Remember, it's always moving along this ellipse. So if it's moving a large distance, small distance, where is it moving the fastest relative to the moon? Where is it moving the slowest? We can tell that right away just by looking at that graph. So, excuse me. What we see here then is that we can answer all those questions down to the answering up down on page 93 down through 6. But we have to ask the question, if it changes, and it does so in the manner that some places is moving fast other places it's moving slow relative where the moon is. Why is that the case? And so I'm going to do a second lecture for the second law because it's more technical and we have to give some time. And it's related to something called the angular momentum. And we see on page 93 where that is. So to finish up law number 2, Kepler's second law, we really need to talk about something called angular momentum. And once we talk about that, then we can finish up page 93, work on page 94 and 95, and then we get to the final law, which is Kepler's third law. And Kepler's third law really doesn't require much drawing. We have to use some of the results and that we've already discovered. I'm going to give you something that so that you don't have to find it yourself. And then what you have to do is make kind of a nasty little calculation. But the calculation is kind of cool. Knowing what we've measured, we can actually calculate the mass of the moon and then compare it to the true and actual mass that we know the moon has. And then you compare the two by something called a percent error, not difference. Because in percent error, we are comparing a measurement to a true value, whereas percent difference is measuring two measured values together, or comparing two measured values together. So, what's next? I'm going to go ahead and stop this video. I'll load it up, and then I'll do a second video to finish off the second law. Once that's finished, then there'll be a third video that will be done today, which is the third law. And that'll be the last of the videos for this particular experiment. This is a tough experiment. It's a long one. So please get on to this and get going. I'm going to look at the due dates. Right now, the due date is a week from this coming Monday. But I'm going to take a look at that and verify that you guys are having good luck with everything. Okay, so I will talk with you soon, and keep watching the videos, keep aware of things, and we'll get this work done. Hey guys, take care of yourselves. Talk soon.